Hello everyone. So welcome back to our latest lecture session. So we have started discussing about buffer intensity, right? And without further wastage of time, let's go through. So we are talking about buffers, and then we discussed the relevant aspects in detail, and now we are trying to derive or look at how to get the relevant equation for buffer intensity, right? Buffer intensity. And we know that it's going to be inversely proportional to the change in pH when you add an acid or base. So instead of H plus, we are going to have derivative with respect to H total. So what is that going to be equal to? It's going to be equal to minus dH total by dpH, right? So by chain rule, what is that going to be equal to? Minus dH total by derivative of H total with respect to H plus into derivative of H plus with respect to pH, I guess by the chain rule, right? So this is what we have. So we are going to look at the two variables here, or two sets of derivatives here. So first we are going to look at dHT, derivative of H total with respect to H plus. So derivative of H total with respect to H plus. But for that, we first need to express what H total is, right? For that, we need to be able to look at one particular scenario. So let's consider scenario where we have a strong acid HA and a relatively, and a base, I guess. Okay, so this is the situation that we are considering. We have these two in our particular system. So from our background, we know that H total is going to be equal to concentration of H plus minus the concentration of OH minus and the protonated forms of both the acids, let's say. So HA and HB, right? But keep in mind that B is a weak acid while HA is a strong acid. So because we are assuming that, what is it now, that HA is a strong acid, right? So we know that when it's a strong acid, it will dissociate at almost all the pH ranges. So we can assume that the HA concentration, or we know that the alpha naught is going to be negligible. So you are going to assume that it's going to be 0. So that's H total is now going to be equal to concentration of H plus minus concentration of OH minus plus what is this now? The protonated form of B, right? So now we need to calculate the derivative of this H total with respect to H plus. Let's work that out in the next set here. So we have dH total by d derivative of H plus, right? And what is this H total? Just for my memory, I'm going to write it down here. It's H plus minus OH minus plus HB, and let's try to simplify that. That's going to be equal to, as you know, H plus minus KW by H plus plus the protonated form, right? So alpha naught of B into B total, right? Again, we know that alpha naught will give us an idea about HB by the deprotonated form and the protonated form, or the total acid, right? So that's what we have here, and that's what we are using this. And we know that B total is going to be equal to HB, and that's how we end up with here. And obviously we also know that alpha naught can be expressed as what now? H plus by H plus plus K, K being the acid dissociation constant for HB, right? HB dissociating to H plus and B minus, and the relevant acid dissociation constant is K. So let's plug this in here. H total is equal to H plus concentration minus KW by concentration of H plus where is this alpha naught? Alpha naught is concentration of H plus by H plus plus K into B total. And now the derivative of that particular equation, that's what we are going to look at here. That's going to be equal to 1 minus KW by H plus square, is it? Okay, right, it's going to be plus, and then now we have f of x by g of x. So if we are going to look at that particular case, how do we go with that? D by dx of function of x, pardon me, gx. How do we go with this? So I think it's going to be equal to first derivative of function of x into g of x minus f of x into the first derivative of g of x by the square of g of x, right? I believe this is what we have. So let's try to plug that in here. So f of x derivative, which is h plus here, so let's say that's going to be equal to 1 into g of x is h plus k and a negative symbol here, and f of x is again, so let's have this in these brackets, f of x is now h plus, and g of x derivative is again equal to, I guess, 1, right? Yes, and the denominator is now equal to h plus k whole square into b total, right? So let's try to simplify this here, and now we are going to have 1 plus kw by h plus square plus k I guess, right? K, because h plus and h plus, k by h plus square, h plus, pardon me, plus k whole square into b total. So this is what we end up with here. So that's one equation we need to refer to later on, right? And the other aspect I believe that we had to calculate was, what is it now? dh plus by dph, right? So derivative of h plus by, or with respect to pH. So for that, though, I am going to look at calculating the derivative of pH with h plus, okay? And what is that going to be equal to? We know that pH is minus log h plus, right? And so that derivative is what we are trying to look at here, right? But we know that, you know, integrals and derivatives, we can't look at log to the base 10. So we need to transform this into natural logarithms, right? So how do we do that? So we are going to look at d by dh plus minus log h plus to the base e, which is a natural logarithm, by log 10 to the base e. Here log means log 10, right? So this is what we have, and let me try to continue this in the next particular sheet. So we are trying to calculate dph by a derivative of pH with respect to h plus, and I believe we end up with d by dh so this is what we ended up with, right? Let me just double check that, right? So now that's going to be equal to the derivative with respect to h plus minus natural logarithm of h plus by 2.303, right? And so that's going to be equal to minus 1 by 2.303 into 1 by h plus, right? So that's what we have here. But keep in mind, I guess we are trying to calculate minus the derivative of h plus by with respect to pH, the derivative of h plus with respect to pH. So now that's going to be equal to 2.303 into h plus, right? So this is what we have. But again, keep in mind, what were we trying to calculate? We are trying to calculate this particular variable. So let's try to plug that in. The buffer intensity, I guess, the beta will be equal to what now? Minus 1 by the derivative of pH with respect to h total. This is what we had, right? And we express this as minus dh total with respect to h plus into derivative of h plus with respect to pH, right? This is what we expressed it as. And so let's try to plug in the relevant values here, and this particular value is 2.303 into H plus, and what is this particular variable here? I think we have that written down somewhere. I think it was 1 plus kW by H plus square, right, plus B total into K by H plus K whole square. So, let me just check that out please, and 1 plus kW by H plus square plus K into B total by H plus K whole square. So, we are on the right track. So, taking this in, it's going to be equal to 2.303 into concentration of H plus kW by concentration of H plus B total into, now I am going to express this in terms that we are going to be able to simplify later, by H plus plus K into K by H plus K, right. And obviously, as you see here, this particular set of variables would be equal to alpha naught, and this particular set of variables would be equal to alpha 1, right. So, let us simplify what we have here. We now have buffer intensity beta is equal to 2.303 into the concentration of H plus kW by H plus would be what now? OH minus concentration plus B total into alpha naught into alpha 1. So, this is the take home message, right. So, the buffer intensity is going to obviously depend upon 4 variables. What are they? H plus, OH minus, the total base present, alpha naught and alpha 1. Again, the assumption here we obviously looked at was HA was an strong acid, right, and we looked at NAB where B is a weak acid, let us say, or HB is a weak acid. So, that is something we looked at. So, we need to look at, we are going to analyze this system further, but we are going to consider 3 aspects here, or the 3 regions in which or at which you are going to have a good buffer intensity, I guess. So, right. So, what are these regions? We are going to try to identify them. So, what are the variables here? H plus, OH minus and alpha naught and alpha 1 and obviously B total. So, think of this now, when the H plus concentration is high, the buffer intensity is going to be high, right. So, when the H plus concentration is high, the buffer intensity is going to be high. So, what does that mean? So, when the pH is less, or in those regions when the pH is very less, let us say less than 3 or so, right, you are going to have a high buffer intensity, right. So, that is what you see. And why is that? We are going to try to understand that later. Again, the other aspect is when the OH minus concentration is high, you again see that the buffer intensity is going to be high. So, again let us say when the pH is greater than let us say 11, right, again you see that the buffer intensity is going to be high. So, we are going to try to understand this, but let us just plug them in now. And this is the critical aspect where the role of your particular acid or base that you plug in is going to come into play. So, let us say for a particular system, let us say you control B total and that is going to stay the same for that particular system, but alpha naught and alpha 1 that they will change with pH. So, we need to look at in which case will the product of alpha naught and alpha 1 be the maximum, right, and we know that alpha naught can go from 0 to 1 and again alpha naught 2 can go to from 0 to 1, right, and also we know that alpha naught plus alpha 1 is equal to 1, right. So, if you look at it, it is going to be maximum only when it is 0.5 into 0.5, which will be equal to 0.25, right. So, only when alpha naught equal to alpha 1 is equal to 0.5 will we have a maximum value here, right. So, only when alpha naught equal to alpha 1 equal to 0.5 will we have buffer intensity to be maximum. So, what is that about? We will try to understand that now, right. The buffer intensity is going to be high. So, again what is this about? We know that ionization fractions give you an idea about the concentrations of the relevant acid and the base, right, the protonate and the deprotonate forms. So, we know that when alpha naught and alpha 1 are equal and equal to 0.5, what does that mean? It means obviously that the concentration of your protonated form is going to be equal to the concentration of your deprotonated form, right. So, obviously it makes sense. So, when you have equal amounts of acid or base present, or and base, pardon me, not or, and base present. So, when you add any additional acid or base, the system can either consume the proton or release a proton to be able to resist the change in pH, right. So, for that you obviously need to have both the acid and the base, and that particular scenario will be relevant to having a higher buffer intensity, and that obviously is the case when pKa, right, when the pH is equal to pKa. So what is this about? When is alpha naught equal to alpha 1 or HA equal to A minus? We know that from our speciation diagram, let us say, and if this is pH and this is the concentration, what do we know? We know that this is the behavior of your HA and this, let us say, is the behavior of your A minus, and when are they equal? They are equal when the pH is equal to pKa. So what does this mean? So when the pH is equal to pKa for that particular compound or the conjugate acid and base, the buffer intensity will be the maximum. So this is the take home message that we have from this particular equation here, right. So now we are going to try to plug this into two systems, right. So one case would be for the monoprotic acid for, let us say, acetic acid, and then we are going to look at the buffer intensity for a particular scenario, and then we are also going to look at, let us say, the diprotic acid, let us say the carbonate system, and look at the buffer intensity or how it changes with pH. So again, initially we are going to look at how the buffer intensity changes with pH, right. So for that, I believe I already have the relevant sheet to save upon time here. Okay, so let us go back to here. So here I have acetic acid here, right, and we know that the pKa is 4.75. So I plugged in the relevant formula for alpha naught, which is the concentration of H plus, right, which is here, H plus by H plus plus 10 to the power of minus pKa, which is K, right. So that is what you have here, and I have pH here, and buffer, total buffer, I am taking it to be 0.1 molal, and this buffer intensity has been calculated here, right. So we are trying to calculate the buffer intensity and how it changes with what do we say, pH, right, for which system now, where we have acetic acid and the total base or total acid present is 0.1 molar, I guess, right. So here I already set it up so that we can save upon time. So the pH is from 0 to 14, the total acid or the base is obviously going to stay the same, and the pKa for the acetic acid, what do we know that to be? It is going to be equal to 4.75 or 4.76. So I am taking or considering 4.75. So here I have alpha naught, alpha 1, H plus, pH, B total, and buffer intensity. And buffer intensity, this has the relevant equation which we just derived, 2.303 into concentration of H plus, concentration of OH minus, into B total plus B total into alpha naught into alpha 1. So that is what we have here, right. So let us try to plug in the relevant values, and alpha naught is H plus by H plus plus K, alpha 1 is K by H plus plus K. So that is what we have here. So let us try to plug in the relevant values here. Okay, so I was able to get a hang of that now finally, and alpha naught and alpha 1, and finally the buffer intensity, I guess. So we looked at alpha naught, alpha 1, and now we are trying to get at buffer intensity. So I am just trying to calculate the formula, or okay. So I already plugged in the relevant data here. So we have a graph here, right, and first try to analyze the data here. So alpha naught obviously at the lowest pH is going to be 1. What does that mean? All the particular total acid or base is going to be in the protonated form, right. So that is what we have there. And alpha 1, where is that? That is here at the highest pH 14. We know that alpha 1 is A minus by HA plus A minus. What does that mean now when alpha 1 equal to 1? That means that all the acid or the base is present only in the deprotonated form. That is what you see here, right. As pH is increasing, alpha naught is decreasing, and as pH is increasing, you see that alpha 1 is increasing. So based on that, we calculate the buffer intensity here, and so obviously it is varying, and here we have a graph where we have y axis is buffer intensity, and on the x axis we have the pH. So the graph, I only asked for it to be showing from pH 2 to pH 12, right. So what do you see here? So we see that we know that the pKa is 4.75, and from our equation we know that, let us have a quick look at our equation. What do we know? We know that it should be high at alpha naught equal to alpha 1, right, which is this third aspect. Alpha naught equal to alpha 1 means pH is, when pH equal to pKa, you are going to have high buffer intensity. So let us see if we are able to observe that here. So when you know that pKa is 4.75, so let us say I am assuming that somewhere here, and you see that the buffer intensity is maximum at, or high, I would not say maximum, is high at when the pH is equal to pKa, right. And again, why is that? At this particular point when pH is equal to pKa, you observe that alpha naught and alpha 1 are the same, or you have same concentration of Ha and A minus, right, or the CH3COOH and CH3COO minus. So, when let us say acid is added, right. So, let us just consider this case. So, you have equal quantities of CH3COOH and CH3COO minus, right, and when you add an acid, right, what does that mean? You are putting in H plus. So, your acetate ion, right, CH3COO minus can take the proton, right, and go into the deep protonated phase, right, but now there is no change in pH. But if you add a base, let us say, or let us say you are putting in OH minus, the acid which is CH3COOH can release its proton, right, and that can take care of the base that you are putting into the system. So, again we are going to look at that again later. So, that is the explanation there. So, that is what is happening out here. But the other key aspect is to notice that at low pH or at high pH, you again see an increase in buffer intensity, right, and why is that? So, what does this mean though? At pH we know is minus log H plus, right, and what does this mean now? For any change in H plus to occur, you need to put in a lot of acid or a lot of H plus, right, to be able to change the pH, or similarly add a considerable amount of base to be able to change the pH. Why is that? Keep in mind pH means it is a logarithmic scale, right. So, here at this particular extremes, you need to add a lot of acid or a lot of base to be able to change your pH. So, again same case here at the higher pH, when it is around 12 or higher than 12, it is going to go up like this, right, until 14. So, again it is logarithmic scale, right. So, at that particular point when pH is 13, let us say, the OH minus concentration is very high. So, you need to add a lot of H plus or a lot of OH minus to be able to make any further change in the OH minus concentration or the pH. So, this is what we looked at. So, let us just try to understand that once again in our system here. I believe I have graph, yes, right, this is the graph here. So, again what is this now? This is the point where, and let us write down the buffer intensity equation here, that I believe was equal to 2.303 into the concentration of H plus the concentration of OH minus plus what else please, B total into alpha naught into alpha 1, right. I think I got it right, right. So, this particular region, what is this relevant to? It is relevant to this particular set of variables here, right. When the pH is equal to pKa, that is when you will have the maximum buffer capacity or intensity, pardon me. Or if you go to the other extremes, let us say in this particular region, let us say, right, you again see that the buffer intensity is going to be maximum. Why is that? That is because of this particular variable where you see that when the H plus concentration is high. So, in this particular case or regions, you know that H plus concentration is very high already, right. So, to be able to make any change in or further change in H plus, you still need to add a lot of H plus. So, that is why you see that the buffer intensity is relatively high in this region, but obviously it is in the extreme regions of 0 to 2 or so pH. And same case here between 12 to 14 or 11 to 14, let us say, again the buffer intensity is going to be high in this region. Why is that? That is because of this variable, because OH minus concentration is high in this particular region, right. The OH minus concentration is very high when the pH is between 12 to 14 or 11 to 14. So, to be able to make a further change in your pH, right, what do you need to do? You need to add a lot of H plus or a lot of OH minus. So, that means the system is a good buffer in this particular region. But obviously rarely would you try to have have a system that is good, well buffered in either the low pH or high pH ranges. You usually look at ranges from 2 to 12, right. So, what is the key here? You need to be able to choose a buffer, right, whose pKa, right, is almost same as the pH where you want to have a good buffer, right. So, for example, in which regions will this particular system act as a good buffer? In the usual regions of pH. So, only when pH is equal to pKa, which is in this case for acetic acid, this is for acetic acid, keep in mind. So, this case was 4.75 or 4.76, right. So, that is what you see here, right. But let us say if I wanted good buffering at around pH 7, let us say, right, I wanted good buffering at pH 7, would this work? So, let us look at where pH 7 is, it is here. So you see that the buffer intensity is very less, right, at this particular pH 7. So acetic acid is obviously not a good choice when you are going to try to have a system that is well buffered at pH 7. So what do you need to do? You need to obviously look for an acid base system whose pKa will be nearer or equivalent to 7, near 7, right. So that is the take home message here again. So we need to choose your buffer based on where the pKa value is, right. So let us look at also the multiprotic acid. Let us choose the carbonate system because we have looked at that in great detail, and so once we are done with that we can wrap up today's session, right. So let us see where we are. We will go back to Excel again, right, and here I have the relevant aspects for carbonate system. So what do we have here? We have alpha naught, alpha 1, alpha 2 because it is multiprotic or diprotic, that is why we have 3 ionization fractions. Again same case as earlier, H plus, pH and B total, that is what we already had earlier. And buffer intensity, now the formula is going to be relatively different. Let me try to write that down here. For a multiprotic system or diprotic system, let me try to 2.303 into concentration of H plus concentration of OH minus, same case as earlier, plus what else here, B total into alpha naught alpha 1 plus 4 times of alpha naught alpha 2 plus alpha 1 alpha 2. So again let us try to identify or understand this particular system. So we already talked about these two variables when the pH is at its extremes. So we are concerned with this particular system. So again we know that alpha naught, alpha 1 and alpha 2 are the ionization fractions which give you relative concentrations of what now, H2A, HA minus and A2 minus, right, the relevant concentrations with respect to the total acid here, right. And what is the total acid in this case, which is B total, which I am a different nomenclature here, B total there, but that is fine. So that is equal to, as we know, H2A plus HA minus plus A2 minus. Anyway, it is giving you an idea about which particular form predominates, right. So again keep this in mind when we look at this data, and with our background we can eliminate this variable. Why is that? Whenever H2A is at higher concentration, A2 minus will be at remarkably low concentration, right. So again try to think of this variable 4 alpha naught into alpha 2, right. Alpha naught gives us an idea about the fraction present as the most protonated form, and alpha 2 gives us an idea about the most deprotonated form, right, which is A2 minus, and also the other case alpha naught refers to H2A, right. So when one is high, the other one would be almost 0 and vice versa. So we can more or less end up neglecting this particular set of variables here. So what are we left with? We are left with B total into alpha naught alpha 1 and alpha 1 alpha 2. So again this is the same case as earlier. So you will see maximum buffer intensities at 2 cases, right, and what are they? When alpha naught equal to alpha 1 equal to 0.5, or what does that mean? When H2A concentration is equal to HA minus concentration. So that is one case. And what is the second case? When alpha 1 equal to alpha 2 equal to 0.5, which more or less translates to the concentration of HA minus being equal to the concentration of the most deprotonated form, right. This is what we have. And when does this occur? This occurs obviously when the pH is equal to the first pKa 1, and this occurs when pH equal to pKa 2. So let us try to understand this with respect to the graph. And where do we have that here? We have that here. So so pKa 1 is 6.3 and pKa 2 is 10.3. I think they are approximate values for the carbonate system. So you can let us go with that. And I plugged in the relevant formulas. So let us try to go through. So now we were able to calculate alpha naught, alpha 1 and alpha 2. As you see, with increasing pH or increasing or lessening concentration of H plus, what do you see? You see that alpha naught decreases, and you see that alpha 1 increases to a certain point in time, or point with respect to pH, and again decreases. Alpha 2 keeps on increasing to its maximum of alpha 1, right. So again let us calculate the buffer intensity here. And now we have a graph, and let us try to understand or look at this graph. So, x axis is the pH, y axis is the buffer intensity, right. So, what do we see here at the extremes, you know, pH less than 3, we know that again it is a system is well buffered. Why is that? And again why is that? Because the H plus concentration is high, and same case at pH greater than 12, you know, this is going to go up again. So, let us this is the graph that we came up with. I think I have that in my particular slide. So, let us go back to the slide. So, this is going to be again going up like this, and this too will again go up like this till 14. So, again what are the cases we are going to look at? When pH is equal to pKa 1 and also when pH is equal to pKa 2. So, obviously we see that the buffer intensity is going to be maximum at those cases, but we see that these are the two relevant points here. And so, when I look at where that goes to, I see that that is more or less, or it should be 6.3, which is the pKa 1 of your carbonate system. And here if you look at that, it should be 10.3, which is pKa 2 of your carbonate system. So, more or less the take home message is that the diprotic acid acts like as if you have two different buffers in the system, right. So, one is with respect to H2CO3 and HCO3 minus, and the other is with respect to HCO3 and CO3 2 minus. So, in this particular, you know, at this particular pH, which forms predominate? You know that H2CO3 and HCO3 minus predominate. So, this will act as the acid when required, this will act as the base when required. And at this point, what are the relevant conjugate acid base species? They are going to be HCO3 minus and CO3 2 minus. So, at this particular point, HCO3 will act as the acid if required, and CO3 2 minus will act as the base if required. So, thus you will have high buffer intensities, which you see here, right, at when the pH is equal to the pKa. So, I guess with that we will end today's session, and we will continue this forward in the next session. Thank you.